Hi class, we are moving on to the next section of the Laplace Transform. Today we're going to cover chapter 7.3. We are going to discuss the first portion of some of the operational properties. So far we've talked about how to transform functions, looking at the inverse transform, looking at how to transform a differential equation, and obviously different things pop up. There's things that we haven't talked about yet. So we're going to talk a lot today about some of the translation theorems. So if you remember what a translation is, it's basically when you are shifting a function. So we can talk about shifting the Laplace transform in different ways. So that's really what we're going to talk about today, as well as a couple of different other things. And we're about halfway through our discussion of Laplace, so we'll keep it moving. Okay, so today is chapter 7.3, operational properties number 1. Okay, so the first theorem is our first translation theorem. Okay, if we have the Laplace transform of a function equaling capital F of s, right? So we're transforming it from t to s, and now again this is a more algebraic function. A is an element of the real value, so it's a scalar. Then the Laplace transform of e to the at times our function gives us a horizontal shift in our Laplace transform. Okay, so basically what we're doing is everywhere that we would normally have s, we're going to replace that with s minus a in the transform of our function, right? So basically what we're doing is, instead of transforming a regular function and getting f of s, right, we are, if our transform has e to the at times our function, right? So if we have a function times a function, in this case a specific function, we'll talk about later on generalizing a function times a function in the Laplace transform, then basically what this exponential function does is it shifts the Laplace transform function over a unit, right? And so remember that these functions are exponential in form, right? So our Laplace transform is the integral of e to the negative st times ft. So what this does is it gives us an additional shift, because now we have e to the negative st times e to the at times ft in that integral. So that gives us a horizontal translation, because we're adding those exponents basically, right? Negative s plus a, so that gives us a change in our variable when we take our integral. Okay, so that's one way to think about it. Maybe I should have wrote that down. Oh well. Let's go through an example. Okay, if I have the Laplace transform of e to the 2t times cos 3t, I'm basically just going to look at the Laplace transform of cos times 3t, and then I'm just going to apply the shift of s minus 2, right? Because my a in this case is 2, everywhere I would have in that regular function, right? So I know that the Laplace transform of cos 3t has this form, s over s squared minus 3 squared, or 9. So what I'm basically going to do is, everywhere I see s, I just replace it by this s minus 2 value that I have. Okay, so everywhere I see s, I'm just going to subtract 2. I'm going to keep it inside of the square function, right? Because s is being squared, so s minus 2 should be squared here, right? So the inverse form of this, very, very simple. You're just going the opposite way, right? So the Laplace inverse form of f of s minus a will give you e to the at ft, right? So here's an example of that as well. Let's do the Laplace inverse, the inverse Laplace form of 2s plus 5 over s squared plus 6s plus 34. So first things first is, it's not very clear what my function is here that I'm inversing, right? So I need to get this into one of my standard inverse forms, right? Either as an exponential function, as a sine, a cosine, some variable to a power, right? I just got to really break this thing down. We've done this before, right? Our denominator in this case does not factor well, right? The only multiples I have of 34 are 1 and 34 and 2 and 17. Neither of those can get me 6. So since I cannot factor this nicely, I'm going to complete the square, which, if you notice, will get me to some form similar to this. So my goal is to complete the square. I'll put it in this vertex form of a quadratic, and then my goal is to manipulate my numerator so that my s term is adding or subtracting whatever is happening when I complete my square here, right? Okay, so if we take our term here, basically we have 6 over 2a, right, which gives us 3. Square that gives us 9, so we add and subtract 9 in the middle. And we combine this to be our outside term, right, our horizontal shift basically in a quadratic, and then we can factor this to a perfect square, right? So we're going to get s plus 3 squared plus 25 as our denominator, right? So now what I want to do is I want to try to adjust this numerator so that it matches with this s plus 3, very similar to what I had here, right? I need to have top and bottom, and then I can talk about taking the inverse of my Laplace function here and bringing it back into the world of t. So, okay, we need s plus 3 in the numerator. So what I can do here is I can start to move things around just like it did on the bottom, right? So I know 2 times 3 is going to be 6. So if I add plus 3 inside of this 2 times s and subtract 6, I haven't changed the value, right? So 2s plus 5. Here I have 2s plus 6, and I'm subtracting 6. So it matches up, right? So this is just going to give me a -1, obviously. And now I have this. So again, I'm not in the exact form that I want, but I'm getting closer, right? So what I can start to do now is I can start to break this apart, right? I want to separate it into my 2 pieces. This -1 over s plus 3 squared plus 25 gets its own thing, and the 2s plus 3 gets its own, because I can have 2 come out as a multiplier, as a constant scalar on the outside, and I have something nice here, right? It'll look like literally just like this, okay? But instead of minus, it'll be a plus, so instead of cosh, right, we're probably looking at a sinh there. Same thing here. Okay, this gives me the form of, I can't really remember, I think it's a sine, right? So regardless, I need this 25 in this case to be the same as the numerator, so we can do our little trick where we're multiplying by 5 over 5. Okay, so now this matches up and these are matching up, so this will give me one function and this will give me another function for the inverse, right? So this will give me a cosine and this will give me a sine, because they're both positives, right? So remember, when it's a negative, right, you're going to get your sinh and cosh when you have your s plus k on the bottom, so you're looking at your sines and cosines depending on if it's s on top or k on top, right? So that is our first inverse Laplace transform, okay? If we look at another example, let's apply this to a differential equation, right? So I have y double prime minus 4y prime plus 4y equals t cubed e to t, and my initial conditions, right? So remember that the Laplace transform is wonderful when our initial conditions are centered at x equals 0, because this the transform of the derivatives gives us a lot of y of 0 values, right? So it's nice when we have these things because it lets us simplify it quite nicely. So let's take the Laplace transform of each term in our dE. So it'll look something very similar to this, okay? So notice again here on the right hand side, I have a function f of t times e to the at, in this case e to the 2t. So we're going to end up doing something very similar to what we just did, right? We're going to do a transform with that horizontal shift and that inverse transform with the horizontal shift, okay? So again, this is just, this translation theorems are allowing us to solve more problems than we would beforehand, right? I think beforehand, we would probably just need to throw this into the Laplace transform and integrate the whole thing in order to see what we're going to get, which can be very, very tedious, right? So we're going to take this Laplace transform, okay? So we know that the second derivative breaks down in this fashion, s squared times capital Y of s, and then your actual function of y of zeros evaluated at 0, which is again nice because we have these values. Okay, so these will both end up going to 0 because of the conditions we have. And then I can start to do the Laplace transform here. So here, this is going to give me another s capital Y times y of 0, right? And then my 4y of 0, right? So I have this going on, and then the Laplace transform of the other side. Okay, so here we go. That's from this one, right? So this is from my 4s here. I think this should, I'm subtracting a negative, so that's why this is positive. Then this gives me another 4 capital YS, and then I'll transform this right hand side. So I know that this is 3 factorial, okay? And this will give me s minus 2 shifted to the 4th power, right? Because it's e squared, right? So when you do these, you should definitely have the Laplace transforms we have so far handy. Also, if you have an actual physical copy of the book, there's a whole list of transforms in the back. I think it's like 100 transforms or something like that, 50 transforms. It's a lot, okay? So here we're trying to isolate the y(s) function. So we apply our initial conditions, so 0, 0, 0. So then we're really just looking at the coefficients in front of the capital YS functions. So I got the s squared minus 4s and plus 4 here. And then I can simplify this, right? 3 factorial is 3 times 2 times 1. I can keep it as 3 factorial if I want. However, it'll probably be easier to deal with it like this. So again, remember I'm trying to isolate y(s) here, so I'm going to divide both sides by this thing here, okay? Notice again that this is also a perfect square of s minus 2 squared, so I'm going to get s minus 2 to the 4th power here when I move it over, okay? So I can try to take this and apply my inverse Laplace transform, okay? So y of t gives me the inverse Laplace transform of this, and I can just start to simplify this thing, right? So I can do my little deal where I pull out the constant of 6, multiply times 5 factorial over 5 factorial, because again, this is looking like e to the t times a t to some power, right? So here, this is actually to the 5th power, e times 2t times my constant, right? So when I simplify this with the 6 on top over 5 factorial, this is going to leave me with 1 over 4 times 5, because again, remember, this is 3 factorial, so I get 4 times 5 left over, or 1 over 20. And that is my answer. Okay, so let's go over another definition. It's called the unit step function. So this is a very important function. We also call it the Heaviside function. So the Heaviside function is given by this fancy u, t minus a. So this is, again, it's some function with a horizontal shift. This function is basically 0 everywhere except at a. And once I reach this a, this horizontal shift right here, right, of a, I then have a value of 1. Okay, so I'm 0 everywhere until I have a value of 1, and then I'm going to be 1 forever. Okay, now this may seem like a simple function, but it can be a little bit tricky to deal with. Maybe now it seems tricky to you, like, what are you talking about, Professor Williams? So if we look at a picture, it'll make more sense. I'm 0 until this value of a, where I then have an output value of 1. Okay, now when we start mixing and matching this function together with scalar multiples or function multiples, then we start getting weird things. So this is a very useful function, especially if we want to, for instance, model something like electricity, right? So if I have a light switch and the light switch is off, it is always off until the time I decide to turn it on. Okay, then there is power coming to it, and it has a value of on, yes, right? 0 is no, 1 is yes. Very, very straightforward. You can think about computers as well when you're talking about binary and signals going to different gates. 0 means a gate is closed, 1 means a gate is open, right? So if I have 0, 1, the first gate is closed, there's no electricity flowing through that. The second gate is open, there's electricity flowing through there, right? That's a very common example of the unit step function, but obviously there's more ways that we can use this, right? If I multiply my function times the unit step function, the Heaviside function, basically what it does then is it creates a scalar, not a scalar multiple, but a function multiple of my function, meaning that I will be 0, and instead of being 1, I'm multiplying times my function g of t. I will now begin my function g of t at the value of a, the value where my function now turns on. Okay, and so when we reach that value of a, we evaluate our function at that value of a. Okay, so it doesn't mean our function, it starts at a, but it starts at the value that it would be evaluated at a. Okay, so very, very important that we understand that that's how that works, right? So we're 0 until t equals a, and then g of t begins at t equals a with the value of g of a at the input of a. Okay, g of t minus g of t, the Heaviside transform with the horizontal shift. This means that my function is on, and when I reach this point, okay, so I now have this value, this function here, this Heaviside function, that is adding to my original function absolutely nothing until the value of a, right? So my function goes and does what it normally does until I reach the point of a, where this Heaviside function turns on, and it turning on by subtracting g of t at its value at a, then actually turns off my function at this point. So what this graph would look like is I would have my function g of t, and then at a it would be 0, and then 0 for the rest of the time, because I'm subtracting from my function the rest of its values from a onward. Okay, so very, very important to understand how this Heaviside function works when you start adding values of the Heaviside at different points to your function, or just building a function off of it. Okay, we're actually going to explore that quite a bit, because I feel like that's the hardest thing to get a grasp of. When I studied this in college, I completely was terrible with the Heaviside function, with Laplace and all these things, and obviously I had to go back and study it quite a bit, so now it makes a lot more sense to me. So just think of it as, you know, when it's positive, you're adding to whatever you have already. So in this case, I'm 0 until a value of a, where my function will then begin. Here, I already have my function going, and I'm going to subtract from my function itself all of its values after this point, which will actually sort of kind of switch this around and make me have 0 after a instead of actual values at a. Okay. So let's look at a couple examples of this. If my function is 2 minus 3 times the Heaviside function starting at 2 plus the Heaviside function starting at 3. So what this means is I'm 2, right, until I reach an input value of 2. Then I need to subtract 3 from the value I'm currently at. So I'm at 2. I'm going to subtract from there. That will get me to -1. And that will then run for a distance of 1. From 2 to 3. Remember, this is a horizontal shift. Horizontal shifts, you take the opposite value of what you see inside of the function, right? So this means that I'm looking at +2. Here I'm looking at +3, right? So when I get to +3, I'm adding one value to the value I was currently at. So I was at 2, and then I subtracted 3, and then I will add one more, and I will be back to 0, right? So that's the way the Heaviside function works when you're adding scalar multiples of that to itself. Later on at the end of this video, we'll look at when we have actual functions where this is like x squared, and this is, you know, we'll look at how that affects our function. Okay. So if I have a shift in my original function and I multiply that times the Heaviside function, what that does then is now the first value of my function has been shifted horizontally to a, and my Heaviside function shifts horizontally to a. So now my function no longer runs normal until I decide to turn it on, right? Or runs normal, is nothing until I turn it on, or runs normal until I turn it off. now what's happening is that when this starts, since I have a horizontal shift in here as well, I'm not going to evaluate my function at a. It's going to evaluate at its initial value. Okay, so now these both turn on at the same time. So if this is my original function, right, from 0 to infinity, and it looks like this, the standard Heaviside function would say, okay, at a, we're going to start here. This would be my function. With this horizontal shift going on, I now shift the entire function over, right? So I have a horizontal shift in my function and this Heaviside function that's saying you start at this point. So what this will do, it will shift the entire function to begin at a. Okay. And so then that brings us to the second translation theorem, where we are now looking at the Laplace transform of a function with a horizontal shift times a Heaviside function, rather than a here we go. Okay, rather than just a e to the at, right? So our first one was here, where we shifted the entire function, right, by multiplying it times that e to the at. That's the first translation theorem. So here we're going to talk about the translation being in the function itself and times a Heaviside function, right? So if my function is given by the Laplace transform of a function, a being positive, then the Laplace transform of this form, where I am shifting my function and starting it at a point that coincides with my function, then I have e to the negative as times fs. Okay, so note that if I'm looking at the Laplace transform of just the Heaviside function, right, with no multiple, right, no function tied multiplied times it, it's going to be 1 over s e to the negative as. In a second, we will look at the transformation of a function that looks more like this: a standard function times a Heaviside function, how we introduced this Heaviside, right? So how I would transform something like this. But the most useful is generally this transformation. Okay, so we'll look at both of those, right? So let's look at this one first. If we do an example, let's take the Laplace transform of the function that I showed you the graph of, right? So these ones are just constant multiples of the Heaviside function, so that's a little bit easy, right? So I'm going to get 2 times the Laplace transform of a constant 1, right? Which is easy to do, 1 over s. 3 times the Heaviside at 2, and the Laplace transform of the Heaviside at 3. So we get 2 over s. We're going to have negative 3 over s, e to the negative 2s, and then this will give me 1 e to the negative 3s, right? There we go. So that's pretty easy, right? So looking at the inverse form, again, you're just the inverse Laplace of this will bring you to your function, right? So the function that we had here. So let's do an example of that. So let's say we have s over s squared plus 9 times e to the negative pi over 2, right? So again, now my a is pi over 2, and this function is a cosine function, right? So a is pi over 2. I have s over s squared plus 9, which gives me cosine of 3t, okay? And so when we put these together, right, notice we're doing the inverse here. So really what that's going to do is going to give me a translation inside of my function, right? And then I'm going to have this Heaviside as well, okay? So when I do this, right, that is going to give me cosine 3t minus pi over 2, right? So that's just giving me a horizontal shift. This isn't, I'm not saying that this turns on or turns off, right? So it should look like this. The alternative form of this, right, is when we have just a regular g of t being turned on at some point, right? So I'm going to have this function here, right? It's going to be e to the negative as times the Laplace transform of g of t plus a. So we shift in the opposite direction. Okay. So let's do an example. So let's say we want to write f of t. given as this piecewise function in terms of a step function, then find the Laplace transform for that function that we write as a step function. Okay, so I'm going to have sine of t times the heavy side beginning at 3 pi over 2, right? So I'm off until 3 pi over 2, so it's just sine times my heavy side at 3 pi over 2. So when I do this, I take the Laplace transform of both sides. Okay, now we can do this two ways. Okay, so I can think of this as e to negative 3 pi over s times sine of 2 plus 3 pi over 2, as we saw here, in this alternative form. Okay, there we go. And then we want to find the Laplace of this thing, right? So I know that sine of t plus 3 pi over 2 is the same as negative cosine of t, right? So that's just from some of the identities of sine and cosine. So then I can just do my negative e to negative 3 pi over 2s, and then the cosine Laplace transform, right? Another way of doing this, right, is to try to rewrite this as a shift of t minus 3 pi over 2. So then that way it matches up with my heaviside function, and I don't have to use this standard form. Oops, it should be more than one line, but that's fine. So we'll let this will let us use this form instead of the form that we use, the g of t, right, instead of this one, right? So this is e to the negative as times f of s, which is a little bit easier, right? Because then I can transform this right away instead of trying to find a substitution for this that works for me. Okay, so what I would do is I would do both sides just like I did here, right? And then I can rewrite this as a shifted heaviside function that starts at the same place, right? And again, that's just going with the identity. So I can rewrite sine of t as another trig function that has that shift inside of it already, right? So that would be negative cosine t minus 3 pi over 2. So now my function agrees with my heaviside function. So now we're looking more at this thing, right? I have a shift in my function and my heaviside function both being shifted to the same place, right? So when I do that, it's very straightforward. I get really the exact same thing I got before, right? So this one gives me the e value, right? And then this is coming from the cosine value. So let's do another example. So here we're going to play around with the shifts so that we can kind of look at what these things look like. So this is my regular function. Let's just say that this is the function I have defined. I have a couple of points of interest here, A and B, that's going to allow me to look at my translations using the heaviside function. Okay, so if I have f of t times the heaviside at A, then what that does is it's 0 until A, where it begins at its regular value evaluated at A. So it'll be 0, and then here is what we have. Okay, if I have everything shifted to B, I'm 0 until B, and then I have a start of my original function and its original starting point. Okay, so I'm starting from my initial value. So everything is just shifted over a B, right? So it's not just I'm going to be 0 until my function starts. I'm shifting my function and I'm shifting my start point to both coincide at the same point. So that's the difference between these two. Very, very, very important to understand that, right? So they both have their own uses, obviously. Okay, now look here and notice that my function is normal until I turn it off at A. So I have my function and then I decide to turn it off by subtracting all of its own values starting at A, right? So these are the three cases that we really discussed in the video previously. So it's nice to have some examples of those, right? And so the next ones that we have are us really playing around with this, okay? So here I'm going to have my function and then I'm going to turn it off at B. with the shift that I decided to turn it off at b. So what's happening here is I have my function and I'm turning it off at the value, right? So here I have my function and it's going, and then the place that I decide to turn it off, I need to be shifted to b as well. Okay. Here I have my function shifted to start at a. Okay, so heavy side and my function both shifted at a, so I'm 0 until a begins, right? And then I'm going to subtract my value of it shifted. This should be a b. Apologies, I must have just wrote it too fast. So my function shifted, no, I'm sorry, my whole function has been shifted by a, right? So my function has still been shifted by a, but I'm going to turn it off at b, right? So the whole function has been shifted by a, and I decide to actually start it at a and then turn it off at b, right? So the whole function shifted by a, ft minus a, ft minus a, and then I turn it on at a, right, and turn it off at b. Okay. Here I have my function. It does not begin until a, right? So again, right, this is, remember my function starts with up and then comes down, right? It looks like this. So it's not starting at all until a, right? And it starts at the value it is at a, and then I turn it off at b. Okay, so it starts at a and ends at b. And that's the end of my video. Okay, so I hope this makes sense. I hope these graphs help you to understand this heaviside function a little bit better. Again, this was always kind of the hardest part for me to grasp. So hopefully these graphs and this analysis helps you guys out a little bit.